Okay, this is the 2019 question 9 exam question, which is worth 15 marks, which I think threw a lot of people because it's worth a lot. The average student got 6.6 out of the 15, so 48%. So it's worth being able to do these because you should be able to do better than that. Okay, during exam reading time, I would recommend that you work out what type of question that you've got. We've done this before. So a student designed an experiment to investigate current efficiency. At this point, you don't know what that means, but during the electrolysis of a sodium chloride solution. So we've done electrolysis of sodium chloride before in Unit 3. We looked at when we produced chemicals, what are the 4 different sorts of chemicals that we can produce. So what chemicals are produced during the electrolysis of a dilute solution of sodium chloride, and what happens when it becomes more concentrated? So if we look on our electrochemical series, electrolysis is this pattern, this positive gradient, because electrical energy is being used to produce chemicals. So you have to put energy in. So we have sodium ions and chlorine ions, and water and water. So you can see that the water is a stronger oxidizing agent than the sodium ions. So the water is going to undergo reduction at the cathode and produce hydrogen gas and hydroxide ions. And when you're making sodium hydroxide, which is one of the chemicals that electrolysis of salt is used for, the sodium ions aren't affected and you've produced hydroxide ions. So already at the cathode, you've produced your sodium hydroxide. This particular question is not interested in the fact that you've made sodium hydroxide. It's interested in producing hydrogen as an important gas. At the anode, you're also producing the gas oxygen. Here is going to show up here, so you can see the gas bubbles. He set this up with these being full of water, and then the gas goes up to the top and pushes all the water out. So you can see that this gas is twice the amount of gas as that gas. This is the hydrogen because there's 2 hydrogen atoms for every 1 oxygen atom. So you actually make twice as much hydrogen as oxygen. It's at the positive. So we've got this reaction and this reaction, and when we put these 2 together, you have to balance so that you've got the same number of electrons on both sides. So this happens twice. So you end up with 6 water molecules over here and 4 electrons. And then if you collect everything over here, these 2, the hydrogens and the hydroxides, can get together to make 4 water molecules. Water molecules will cancel out and you'll be left with 2 water molecules, and then these collect, so you'll be left with producing oxygen and hydrogen in a 1:2 ratio. So we can use electricity, and you could get the electricity from a renewable energy source like solar power, hydro, wind, something like that, to use your electricity, and then you make hydrogen gas. And then we might look at fuel cells next. You can then use your hydrogen and react it back in a galvanic reaction in a fuel cell, and the chemical energy is turned into producing electricity then. So these 2 go together. Okay, so the next page. So this question, identify the dependent variable. So the independent variable is what I set up. Remember the I for independent, so whatever you choose, and then the dependent is what's going to happen from that. So if we look, there changing the concentration of sodium chloride solution and looking at the effect of that change of concentration on the current efficiency or on the volume of gas produced. So they accepted if you said the current efficiency would be changed by a change in concentration, but it's better if you write what's measured. So the volume of gas, either hydrogen or oxygen, and it turns out that they're mainly looking at the hydrogen because that's kind of more important, and it's also not going to be affected by this problem that we have over here. All right, so that's the first one. So the next page. Identify a safety risk with chemicals produced during the experiment. So you're making hydrogen, you're making hydroxide in this one reaction here. Hydrogen is flammable and explosive, and this pops up in heaps of exams, so it's good to remember. Flammable meaning that it will react spontaneously with oxygen, and because it's making energy, heat, if it combusts with oxygen, and they're gases that are being produced with a lot of energy, is what causes explosions. And if it's confined in a glass tube, if you're making the hydrogen, then it could break this potentially. So if this was weak, you're making a gas under pressure here. Chlorine's toxic, so you don't want to breathe it in. It's a gas. And hydroxide ions. So on this is where you're making a hydrogen and your hydroxide, and on this one you're making the oxygen, and then eventually potentially chlorine. So they're the risks. So what are the safety measures? Don't have an ignition source. This is a good word to remember. So, or if you can't remember that word, just say don't have any sparks or a flame, an open flame, in case that gives enough energy to overcome the activation energy, and then the hydrogen will start burning. So chlorine, if you're making chlorine gas here, then when you release the stopcock, you should do this in the fume hood or have the room ventilated. So as long as you're kind of referring to something that you're trying to do, it doesn't matter, as long as they can see that it's logical. Hydroxide is corrosive, so wear glasses, lab coat, wash your hands after use. So it's just something logical. All right, the next one. So once you know that you're making hydrogen and oxygen, and hydrogen is in a 2-to-1 ratio when you look at this here, 2 hydrogens for every 1 oxygen, then you can start to recognize what's going on with these numbers. So you're starting with 170 mils, so it's full, and then it's going down because you're producing gas, which is pushing the water down. So you can see this one has made about 70 mils because it's gone down about 70 mils, and this one's gone down about 35. So 35 2 times that is 70. So this, you can see this, the 2-to-1 relationship. So you would realize that this at the negative electrode is where the hydrogen's being made, and this at the positive electrode is where oxygen's being made. These kind of things, that electrolysis of water makes hydrogen and oxygen, should be something that you just recognize and that you're looking for. Okay, so you won't have time to work that out in an exam. You need to kind of be looking for it. So other results, so of labeling precision, that should be 18. I scanned a bit wrong one. Oh well, doesn't matter. So if we look in now here, precision and accuracy, define precision, define accuracy. If you want to see precision, then when you repeat tests under the same conditions, how close they are, you'll be able to see it. If you want to improve precision, then whenever you repeat tests, they have to be under the same conditions. So are the results in part 1 precise? Are they close to each other? So if you've got the smallest ones, 99.8, and the largest one is 100.3, then you can see that they're 0.5 mils apart. You need to say, so the range, this is the range, how far apart they are, and that is a small number, so it's precise. That could be a small or large number, depending on how big the value is that you're looking at the variation of. So if these were all 5 mils, then 0.5 mil from 5 mils is actually 10%. So in that case, a 10% variation is quite a lot. So just saying the range sometimes is not really clear enough to show that they're close together. If we look at our average, so our average is 100, then we've got 0.5 on either side of the average, above and below. I mean 0.5 altogether, and then if you divide that by 2, it's 0.25 above and below. So yeah, above and below. So if you divide that difference from the average and work out the percentage of that from the average, then you can see that that is a small number. So turning the difference into a percentage shows you how close the variation is. So this would be 10% different, and this would be 0.3% different in that case. So this is a better way, although they will accept just a range. Okay, write the half equation that would be expected to be observed at the negative electrode. And remember, our negative electrode is the cathode where reduction occurs. Make sure you have a reduction reaction. This is in your electrochemical series, so because you're just copying it from the electrochemical series, you have to include the states. Which is probably why only 31% of people got that mark. They probably left their states off. So calculate the volume of gas expected at the negative electrode. So they're really focusing here on the negative electrode, which is producing hydrogen, which is why when you start to look at this, even though we're producing hydrogen and oxygen, so the volume of gas, you look at it from terms of hydrogen. This is just Faraday's laws. It's 3 marks. You should be able to do Faraday's laws. You might have got up to this point and not remembered this equation. So we've got our current 2 amps, which is on here. And then if you look in the method, you'll find that you've got 5 minutes. The 5 minutes is a bit vague. It's here after 5 minutes. So it's hard to do significant figures for this question because you don't really know how accurately the 5 minutes was measured. So basically, they're probably not going to give marks for significant figures here. They will give marks at different steps. So when you read the exam answers, just see how many steps did you have to do before you actually got a mark. So if you worked out 600 coulombs, you wouldn't get any marks unless you continued to turn that into the number of moles of electrons. So that's where the first mark occurred. And then you need to use your ratio. So the number of moles of hydrogen, and you've got, that's why they use this, the number of moles of hydrogen compared to the number of moles of electrons. It's a 1-on-2 relationship, so you're going to have half the number of moles of hydrogen. And then you're using this equation, which you need to remember that they're gases, and it says up here that they're under standard laboratory conditions. So as soon as you see standard laboratory conditions, you know that you can use that equation. So rearrange that equation to find the volume expected. This is 24.8 litres for every mole of gas. Cancel and your answer will be in litres. So you would have gotten marks even if you'd stopped here, because it hasn't asked you to talk about the volume in mils. So this or this would have given you the marks. You do need to include your units though. So you can't just put 0.077 because 0.077 watt. You can see this is the mils that we would expect if 2 amps of electrons is put through. Okay, so the percent efficiency is looking at how many mils of hydrogen did you actually make. So the percent efficiency is basically this number divided by the predicted to work out that you'd make 91%. It's 91% efficient. So some of the electrons that are being transferred are not being transferred to the water to make hydrogen. So you can see you're supposed to get 77 mils of hydrogen. You've got 69.9 in pure water. You've got 72 in when you add a bit of salt, and then you've got 74.8 when you add more. If we looked at the of oxygen, and you've got, not very much here, and then it's going up, and then all of a sudden it's gone up more than you should have been making of oxygen. So you're making some other gas here when the salt solution gets really high. And when the salt solution gets past 1, too far past 1, then this starts to produce chlorine. You can see that this reaction would happen twice compared, that's making 4 electrons, so this would have to happen twice to make 4 electrons. So you'd actually make 2 moles of chlorine compared with 1 mole of oxygen. So you're making a lot more chlorine gas if that reaction, a lot more moles, a lot more volume if that reaction starts to occur, which would explain why it's gone up to 70. So what conclusion can be drawn? So conclusions, you need to relate your conclusion to what the aim was. So they said the current efficiency increases as the concentration of sodium chloride increases. Or the measured production of gas increases. So it's always good to kind of refer to the results. So you get 1 mark for showing that there is a trend. As the concentration goes up, the current efficiency goes up. State the change the students should make to their experimental design to ensure they achieve their aim. So their aim is to connect concentration of salt to the efficiency. So you can see that we still haven't got our efficiency up to what it should be, 77 mils produced. So you may as well keep increasing the salt, increasing the concentration to totally see if this efficiency will keep going up, if the hydrogen being produced will keep increasing. So use higher concentrations of salt. So my answer was to say, that's what I'm saying, that the cathode production of hydrogen is still not at the optimum, so continue to see if the trend will increase. Continue to rise as the concentration increases hydrogen. Now we're kind of focusing on the hydrogen. But Vika's saying if we were looking at the production of the other gas, so the production of oxygen, it gets a bit messy the higher the concentration of salt goes, because you're starting to make chlorine. Okay, so even though VCAR, they put answers, this is an acceptable answer in their answers, they'll have a whole range of answers that would be accepted. Vic posted to convey research to state two different aspects of electrolysis that should be included in the discussion. So there's a whole lot of things you need to do this in the discussion. You need to look at your actual data and compare that to the expected, which is what we've been doing. You need to link the data to the theory. So we've been looking at the electrochemical series. So why would you expect, why is this a 2-to-1 relationship? So you need to, it hasn't asked you to do this overall to work out the 2-to-1 relationship, but you would need to have done that to understand it. So in your discussion, you would be talking about a 2-to-1. Analyze the experimental design. So look at what the student's done and errors. So your errors are systematic. So we've got our ammeter, and the ammeter results you see here haven't changed. They're all 2 amps. 2 amps. And when we did electrolysis, you would have noticed that the current, current changes over the time. It will fluctuate, go up and down. And so because it's fluctuating, then the amount of electrons that are being transferred would be altering. So is this accurate? Is this accurate? Was it calibrated? Could it be recorded not only initially but over a period of time? So could you improve the method? Because you're basing your prediction here on a stable 2 amps. The values for the volume are given here, which is weird. They're given to a decimal place. But when you look at this, you can't read that to a decimal place. Each of these is 2, 4, 6, 8, 10. Each of these is 2 mils. So a half of that would be 1 mil. So to measure that in 10 parts to get 0.1 of a mil is too difficult. And we're basing our differences here, we're basing our precision on measuring to 0.5 of a mil, when it's very difficult to use that on this scale. So analyze your experimental design. So look at what the student's done. And errors. So they don't ask you to write about these, but if you said analyze and gave an example, it wouldn't hurt. Methods and an average for the pure water, but they've only done each of these once. So you can't see the precision, can't see how close together your values are if you only do it once. You can't get an average, which is more accurate. Yeah, and then you would discuss further experiments or improvement to this design. All right, sorry, that's gone on and on.